Hello, students. Today we're talking about ratios and proportions. I'm very excited, Mr. Butterworth. Did you know our students have been talking about ratios and proportions since fourth grade?
Fourth grade? Does that mean my daughter's going to see those? Because she is currently in fourth grade.
Wow, she's getting old.
She is. That's what happens. The sun goes around the sky.
Oof, it's crazy. Ooh, man, we've got some transformations going on here, and I noticed that it looks like we have more than one transformation.
We do. This is a little quick review of some of our transformation adventures.
I feel like that means we have to work from the inside out because we talked about doing this kind of backwards feeling.
That's true. I'm going to write down the original coordinates while you talk about what that means.
Okay, so I see this stupid notation that means a dilation of 1.5 times as large as the original, and we have to include that it's about the origin because not being precise is super annoying. And this is for triangle LMN. So for our first transformation, we're going to multiply all of our coordinates by 1.5 to get to our primes.
I did L prime for you. I'm the best.
Cool. And you multiply those by 1.5. M prime is going to be at 3, 6. And n prime is going to be at 6, -3. Let's say -1.
That is not how you multiply, my friend. So now that t is translation, -3, 2. So that's left 3, up 2. So -3 minus 3 would be -6. 2 plus 3 is 5. And then 3 minus 3 is 0. 2 plus 6 is 8. And then 6 minus 3 is 3. -3 plus 2 is -1. So -6, 1, 2, 3, 4, 5, 6. Oh, you're already doing it? Never mind. You do it. So Mr. Carlson already drew, and I'll connect these dots. I like how they give us these pictures, but then we can't actually
It's a good thing that none of us made this.
draw them. I did not make it. I don't know who made it. I'm going to blame Mr. Regis.
I think that's fair.
Seems like a good person to blame. I made that line a little bigger because it's supposed to be along the line there. So we made the blue one and then the red one. Just a quick review of transformations. No big deal. Hopefully that was not anything too earth-shattering.
Oh, now we're going to talk about ratios. It's everybody's favorite thing. We know that we have ratios and we often just kind of write them as fractions, but we have some different ways that we can write ratios. And that's really, at least according to Mr. Butterworth, because I tried to delete this slide, the important part here is that we can write these in a few different ways. And we tend to read them all as A to B in terms of the ratio part. The other thing that I think is really important, and this is a really major hint for something that's coming up, I don't know, in the future, we have to express these things. I'm going to rephrase that. We should express these things in the same unit. Because sometimes people will get a little bit angry if you write ratios that are not in the same unit. Oh,
what
look.
do you mean by the same unit? Sorry, very flipped.
So actually, let's talk about that here. So in this problem, we're talking about a bonsai tree and the full-size counterpart with inaccurate information, where we have a bald cypress, which is a type of cypress tree that, according to this problem, was 118 feet tall. And the bonsai version of this is only 15 inches tall. So if we're talking about the height of the bonsai to the height of the senator, which is a really weird way to say that, it might be that we write this as 15 to 118, except these are different units because 118 is in feet and 15 is in inches.
Is it okay to leave them like that as long as we keep the units?
Yes. This is a totally mathematical acceptable thing. and anyone who tells you otherwise is wrong.
Whoa.
I'm very comfortable saying that statement because that is a true statement, that as long as you have the units here, this is correct. In fact, we see this a lot on like scales of maps, where it'll show like 1 inch is equal to 1 mile in the real world.
That's true. That's true. We wouldn't say 1 inch is equal to however many inches are in a mile.
A lot.
At least 12.
Yeah. So one of the things that is problematic about this is that if we try to write this in terms of a fraction, okay, 15 inches to 118 feet, reducing this gets kind of weird. And to be fair, you can't reduce these numbers at all because these are irreducible numbers. They're relatively prime, as one might say.
Well, so let's use so down the bottom, I put the Wikipedia information before it was burned down, apparently, because the tree got burned down. So they said 125 feet. So if that was the number, you're saying I could reduce that?
You absolutely could. In fact, you can reduce that by 15. Because no, you can't. Because my explanation for that was going to be because 1 + 2 + 5 is equal to 6.
I was like, where's he going with this? Because you can't do that. You can reduce it by a factor of 5 is what Mr. Carlson definitely meant.
So you'd get 3 inches to 25 feet. However, if this were some kind of a standardized test, probably not going to see this written in this way. They would want this to be in inches compared to inches so that we're comparing these two heights in a way that's a little bit more clear to see how different these things actually are, because these are a lot different. So we may need to do some conversions. Would it be true to say that
if we stopped using this ridiculous measurement system that we have and we use the metric system, this scale factor idea would be easier?
Yes.
Okay. Because you have like tens, hundreds, and thousands going on.
Yep.
Now, I want to add an additional question here. So suppose we use the 125 that the Wikipedia told us, because that's the stuff that I put down the bottom there because I didn't know what the senator was. And we use the 125. And then we're told that the trunk diameter is 17.5 feet. If that's the trunk diameter of the senator, could I use that to figure out the diameter of this bonsai tree? Assuming that the scale is the same.
With that assumption, yes.
Because that's the assumption of the problem, is that the scale is the exact same. It's
yeah. The biology of that makes me a little bit uncomfortable.
Oh yeah, I mean, talking about two different trees and one being a scale factor of another is totally wrong. Because a small version of a full-size tree doesn't mean that it's like a replica in small version.
Ooh, you can buy a bald cypress tree at arborday.org.
I'm sorry, Mr. Carlson got distracted. So we're going to use
or Home Depot.
This piece of information that Mr. Carlson came up with. Get out of here. This piece here, I'm going to move it up here, and I'm going to bring this back. So the 3/25. And we're going to say, okay, if 3 inches is to 25 feet, then if I want to talk about the diameter was 17.5 feet. So I'm going to put the feet on the bottom because I think I want to keep units in the same place. So we're pretending that this bonsai tree is an exact replica of the senator, but tiny. So I don't know this. How did I set it up? Did I do okay with that, Mr. Carlson?
That looks good to me.
So then to solve this, this is a division problem. We said that on the previous page. So I want to undivide, which is multiply, by 17.5. And by 17.5.
I'm not comfortable with the way that you put that.
Feet. Is that better?
It is.
Okay. Mr. Carlson was not comfortable because I need the units to cancel out. So in order, and the 17.5 will cancel out, but the feet will also cancel out, so that I will be left with inches as my answer. That's what his issue was. And I am going to go ahead and be lazy and say 3 times 17.5 divided by 25 is 2.1. Okay, that works out. So that means that the unknown height of this no, the diameter, sorry, of this little tree is 2.1 inches.
Cool.
I just wanted to set us up for where we're headed.
I just tried to use my mouse to click again. Okay.
Mr. Carlson, you better do this one because you were in the band.
That's true. So looking at this, we've got a school band. They're buying tulips and daffodils to sell at their fundraiser, and they buy 120 pots of flowers total. The ratio of the tulip pots to daffodil pots, which I'm just going to call tulips daffodils because it's way shorter to say, will be 2 to 3. How many pots of each type of flower should they buy? Here's how I like to set these up, Mr. Butterworth. I don't know if this is the same for you. I know that whatever this is, it could be 2 pots or and 3 pots, or it could be, I don't know, 10 and 15, but it's got to be the same scale factor multiplied by each of these numbers. So the way that I tend to like to write these is that 2 times some scale factor. I'm just going to write that as SF.
You could just use n. That's what they used in the previous
Oh,
stuff.
that is true. So 2 times that scale factor n plus 3 times that scale factor n. And I'm going to go one step further and say that this is going to be tulips and daffodils. And when I add these two things up, whatever that scale factor is, I've got to get to 120. This looks like an algebra problem now.
It does.
And I know 2 plus 3 is 5. So we've got 5n is equal to 120, which means that n would be 24. Okay, but that's not what I need. That's just a scale factor. Oh. But then if we know that tulips, and this is really why I wrote this above there, is 2 times n. So I could say that tulips is going to be 2 times 24 is 48. And that daffodils is going to be 3 times that. Let's put daff. That's going to be 72. When I add those up, I do indeed get to 120. So that suggests that my math was okay. And if I wanted to go one step further and kind of double check the other way, 48 divided by 72. I know both of those are divisible by 2 if I don't know anything else. So that's going to be 24 over 36. I can divide by 2 again, but now I can see these a little bit better. I'm going to divide both of those by 12 and get 2 over 3. That's the same ratio we had at the beginning. So it's like I double checked, Mr. Butterworth.
That's good. If you go to the next slide, I don't know how the kiddos would do that. I don't think they would do what you just did.
Ooh, I don't think they would either.
So here's my guess. This is not all of them. This is some of them. So they would say, okay, 2/3. If I put that in my calculator, I get this. And so I need that to kind of be the number I get when I divide things. So they would just be like, let's do 50 and 70. Because that makes 120. And when they divide that, they would not get this number.
No,
so my guess is that they would kind of adjust up and down from there. I don't know that, but I think that they would do a lot more guess and check type of work than algebraic work.
Yeah. Can I offer another option as well?
Of course.
And that's using this as a table. And I know that I'm going to put scale factor here just to kind of keep track of stuff. And then put total. I probably, as a student, would not have put this scale factor column there. That's totally a teacher move. But we know that 2 and 3 works. That would give us a total of 5, which is way too small. So I might bump this up. That'd be a scale of 1. and maybe do 20 and 30. That'd be
So
a
that'd be a
scale
scale
factor
of
of 10.
10, but that's only 50.
So I might bump this up again, and I don't know, maybe do 100. That'd be 200 and 300. That's way too big. So I might kind of just wheedle between these two. I know 50 is closer, maybe I'll do 20. So then that would be 40 and 60. That gets me to 100. I'm getting a little bit closer.
And then just keep playing with that.
Yeah, and I think this is a totally fine way. This is a great way to kind of keep track of thinking.
Yep.
It's a little bit less random than doing the I'm going to try and divide these two numbers method, which is, again, that's a legitimate path to a solution. Tables help us organize and use a little bit more strategy when we're doing things like guess and check.
And this is similar to the idea of what you just did. So this is just an extended ratio. So it's saying there's more stuff here. It's just a ratio of.
So is an extended ratio just a ratio that the book decided to add the word extended in front of?
Yeah, like it's just a ratio. I don't know why we're calling it extended ratio. It's a ratio with more than two numbers, and that's okay. So this is 3 to 5 to 6. And it's saying the perimeter of the triangle is 98 inches because they're pretending that like they can make this into a realistic thing. Yeah, no one will ever use that word extended there. I don't think. I don't think that's an actual mathematical thing. I think that's what your book made up. But anyway, perimeter is add them up. So that means 3x plus 5x plus 6x.
Oh, because perimeter is the distance around the outside.
Yeah, it's 98. Add up the stuff around the outside. I always like to picture an ant. I don't know why I pick an ant wandering around the outside of a figure.
That makes sense.
And then 3 plus 5 is 8, plus 6 is 14. And that's 98. Divide both sides by 14, and you get some number.
7.
7. Is that right? 7. Yep. Yes. My brain just fell out for a minute. I was thinking 5. I was like, what is going on here? Anyway, and so x is 7. So what is the length of the longest side? So the longest side is 42. And x is the scale factor. So we're going from like a triangle that's 3 by 5 by 7 to a triangle that's bigger than that. I like how you're just editing this as we go. Sweet. So don't be scared if there's multiple numbers, it's okay. Same thing works. And you'll see that when we talk about a concept called similarity.
Yeah, it's also like we have this annoying tendency to try to pretend this is different than the stuff that we did before. But this is just a scale factor, just like we were doing dilations, and isn't really any different. We're just using different language and symbols to describe this.
That is a weakness we have, especially in America when we're teaching math. We like to treat math as individual units instead of everything's combined. Everything's interrelated. We just have to sometimes work to make those connections.
That's true. Okay. So now we got to do some solving. And again, you've been solving proportions since about 7th grade. So hopefully this is a nice review. I have a feeling that Mr. Butterworth and I are going to refuse to use certain words that you have used in the past. And I'm going to start off with A. I'm going to rewrite this so I have a little bit of room to write. And one of the things that I notice, I've got stuff on the bottom of my fractions here. I don't like that. That makes me a little bit uncomfortable. So I'm going to play the get rid of it game. I know if I'm dividing to get rid of something I'm dividing by, I'm going to multiply by it. And that will let me, on the left side, kind of get rid of those. I still don't love having that fraction there. So I'm also going to multiply by 4.
And if that makes you uncomfortable, Mr. Carlson is right here. And then he's multiplying by 4.
Yeah.
If you just need a different way of looking at it.
So that's going to get me to 24 on the left is equal to 5x on the right. Divide both sides by 5. We get 24/5 is equal to x. And I like it.
I'm going to do this part B in 2 different ways.
Ooh, that sounds fun. You mean
So
because those numbers are a little bit nicer to play with?
yeah. So one way that some students will notice is to get from 3 to 9, I multiply by 3. So to get from y to y plus 4, I multiply by 3. And I regret using the x as a multiplication, so I'm going to get rid of that. I multiply by 3, and I multiply by 3. So, oh, did you want to do that in a separate, different way?
I was just gonna do this while you talk about that, then I'll talk about this. 'Cause
Okay. Yeah, no, that's fine. I didn't want to screw you up. So I need to multiply y by 3, and I get y plus 4. So if I'm there, then I'd subtract the y from both sides. And then I divide by 2, so y is 2. That's kind of a more sneaky way of doing that. Well, not sneaky as in bad, but it's just a little bit different. So you have to think a little bit differently about that. If we want, and maybe Mr. Carlson, you should talk about what you're doing now.
Sure, I'm doing the same exact thing. But since I didn't have a clean way of looking at that, like this is times 3, I had to make them be the same. And I'm going to regret saying this, but I had to find some common numerators in order to do so. Because that's where my constants are. So I had to make those be the same. So I made this 30 and 30 by multiplying by 5 and 6, the opposites respectively. We know if we multiply fractions, we got to multiply by the same thing on top of itself. Let's multiply by 1. And that lets me make an equation from the denominators saying that 5x is equal to 24. So in my mind, this is a really kind of the same thing that's going on here. Just kind of without showing that you're doing the 3 times 3 step here. But it's the same thinking to do either of those.
Now, if that made you super uncomfortable, you could also multiply both sides by 9. And the reason I picked 9 is because there's a 9 on the bottom of the left. So the 9 and the 9 cancel out on the left, so you wind up with y plus 4. And then you wind up with, really, remember, that's 9 over 1. So that's 9y over 3. But wait, 9y over 3 is just 3y. And then we're back to where we were before, where we subtract the y and divide by 2.
Would it have been okay if you didn't recognize that these were, that 9's a multiple of 3, to multiply them both by 3 as well?
Yes.
To also get rid of that 3?
Yep.
So you end up getting, 3y plus 4 is equal to 9y.
Mm-hmm.
And you have a little more work to do there, but you end up at the same place. One of the things that I really would like our students to understand from this is that there are so many different paths to get there, that there's not a do this first step, and anyone who tells you that you have to do a step first is wrong.
As long as you're doing logical mathematical moves, you're fine. Mm-hmm. So if you look at us and you say, well, can I do this? We might say, sure. It might not be a useful step. Like sure. If you're solving an equation like x plus 5 equals 10 and you decide to add 7 to both sides, can you do it? Sure. Is it like a logical, is it a good move necessarily? Maybe not. But as long as you're doing logical mathematical things, you'll be okay.
I feel like
a life lesson.
Yeah, I agree. I feel like this is one they might be able to do on their own.
Number A?
I think, because we just did 2 that were similar to this.
That's true. Although I think yours was harder for A. So you think they can do that?
I think so.
Okay.
The other thing I wanted to mention here, one of the things that we deleted was a slide of properties of proportions, because it's not so useful, except if you really struggle when variables are on the bottom. One of the neat things that you can do is take the reciprocal of both sides. These 2 equations are equivalent, and in solving them, you may have an easier time with one or the other. I'm not saying that you will, but this is a thing that you can do that may be useful to you.
I like that you used the word reciprocal, because I think they heard that if they had Miss Callie in 7th grade. Because I think a couple years ago I asked the students and they told me that it was Miss Callie.
I have a friend, Mr. Nystrom, who also uses that word.
I'm just showing you how mathematically you get to what Mr. Carlson just did. In case you're concerned or confused, you may not care, and that's okay. I forgive you. And divide by 3 also. So I wind up with m over 3, and then m plus 1 over 15.
I like it.
Sweet. Last slide. All right. In the diagram, x over 6 is y over 7. What ratio completes the equivalent proportion x over y? Justify. Okay, so this is basically what I was just doing. X over 6 is y over 7. I want to get this y over yonder. Wow, can't I just divide both sides by y?
I think so. That would make sense to me.
Or if that confuses you, you could multiply by 1 over y.
I like that. Actually, I like that quite a lot.
Because that's the same thing. So that gets me x over, I have 6y now, equals 1 over 7. Well, I got us partway there.
Whoa, we're partway there.
No, it's halfway there, Mr. Carlson.
Oh, okay.
So I got to get that 6 out of there. So I can do the same idea, multiply by 6 over 1 and 6 over 1. And you get, I'm going to wander over here, x over y is, remember, multiplying fractions is the easiest thing you can do with fractions. 1 times 6 is 6, 7 times 1 is 7.
I like it.
We did it.
I also noticed that that kind of looks like we can do that in this triangle. And for reasons that we don't know yet, we can basically say, oh, look, I can divide those two and that equals divide by those two. But again, we don't know why that works or what would make us be able to say that about this particular set of triangles.
You're saying that for the future.
The future, where we dilate time.
That sounds great.
Cool.